So we're going to talk about enzymes, and enzymes are proteins. Some of them are even pieces of RNA, but we'll talk about those later. But basically enzymes for now, we're talking about proteins, and they act as catalysts, right? So they act as catalysts. So some things we want to keep in mind: they are not used up in the reaction, or consumed would be one way. Okay, they have an active site, which is where our reaction is going to occur. They lower activation energy, right? So they lower the activation energy of a reaction. All right, and they're going to do this by interactions within the active site. And so the net take home is they're going to speed up reactions so that they occur at biologically relevant speeds or rates. So we like to look at this diagram, and we went over this in class, but let's just go over it really quick. You have free energy on our y-axis, the course of our reaction. So we're going to progress from reactants to a transition state to products. All right. Now, the important piece to this in terms of the enzyme is the energy of activation, or EA. So the blue line indicates an enzyme catalyzed reaction or a non-enzyme catalyzed reaction. So there's no enzyme present. Right? And when we get up here to the transition state, we have increased, right? The reactants were down here in terms of their potential energy. The transition state, they're that amplified state of energy. Then they drop down and we develop our products. What the enzyme does is it lowers the amount of activation energy required. So our reactants only have to reach this lower transition state before they head to products. All right? Delta G, our change in Gibbs free energy, right, is the same whether the reaction is catalyzed or not. Now this is an exergonic reaction, right, because products minus reactants, if we look at the energy in them, all right, we do P minus R, right, products minus reactants in terms of energy. In this case, it is negative. And so delta G is negative. It's an exergonic reaction. All right, so let's look at an enzyme. So we've got a schematic model over here on the left, all right? And so we should really imagine this thing being three-dimensional, but here's my active site, here's my substrate, it enters into the active site, and it will undergo some sort of transformation, all right? Now if we look at a molecular-based model, all right, here we can see our active site, and it looks much more like a three-dimensional cavity. In this case, hydrogen peroxide comes in, all right, and so this enzyme would be called something, it's called catalase. Right, written right here, and it's going to take the H2O2 and it's going to convert it to water and 1/2 O2. All right, that's what it's going to do. So just like if you ever poured hydrogen peroxide on a wound, you've seen it fizz. Well, that's what's occurring. Your body has catalase in it. And so what's happening then is in this active site, as we've talked about previously, the hydrogen peroxide is interacting with the R groups there that's causing the breaking and formation of new bonds. All right, so if we look at the folding of an enzyme, and we've talked about, so we're looking at something with primary structure here, right? And as it gets folded up, all right, what we want to see is everything in purple here, these are amino acids associated with our active site. And the folding brings those R groups, right, and those amino acids into proximity where they can carry out their specific function. And so the little orange one in the middle here, that's our substrate. All right, so some basic things to consider then for our enzyme is is that it lowers, right, EA, all right, and it has this active site where it binds substrate and catalyzes the actual reaction. So we can also think of this as our catalytic site, right? It's where we are actually going to cause this reaction to occur. The amino acids in the active site are generally not located close together in the primary structure of our. All right, so we've discussed how the enzymes function. Now let's talk about how we can control the enzymes. All right, we might want to prevent them from working, as fast. And so some drugs, like sulfa drugs, if you've ever had to take them, they're used as an antibiotic, all right? And so if we have sulfa drugs, all right, so what happens is that we have a substrate, it enters into the active site and it goes to a product, all right? In competitive inhibition, the inhibitor occupies the active site and prevents entrance, right, by the substrate so it can't be acted upon. Now, the inhibitor will leave. It doesn't bind here permanently, and so what happens is that if you have a higher concentration or a high concentration of inhibitor, you can saturate the enzyme and prevent the substrate from being made into product. All right? If your concentration's too low of inhibitor, all you will do is slow down this reaction. Okay, so that's competitive inhibition that occurs right at the active site. Now, in non-competitive inhibition, we have what is called an inhibitor site. The inhibitor site is what we also call an allosteric site. Allosteric referring to just an alternative site. All right. So in this case, we have an inhibitor site, we have an active site. So when the inhibitor site is not occupied, the active site on our enzyme has the proper shape. In comes the substrate, it gets acted on, it goes to product. All right. However, if the inhibitor is present, it will bind to our inhibitor site. It will alter the shape. Right? It's going to alter this shape here of our active site, and it will no longer act upon the substrate, and we will not get, right? We will not end up at product. All right. So that is non-competitive inhibition because it's not competing for the active site directly. And then finally, we want to talk about an allosteric activator, an allosteric inhibitor. So we can have inhibition or turning this thing on. All right, so if we look at a pathway, so this is a metabolic pathway, we're going to go from threonine to product 1, product 2, product 3, product 4 to isoleucine. Threonine and isoleucine are amino acids. So what happens is that we're interested in this threonine dehydratase, and what happens is that since this is the first step in this long metabolic pathway, this first enzyme is the one that gets regulated. All right? Wouldn't make much sense to regulate the last one, right? You want to start, since we're looking at the production of isoleucine here, we want to sort of allow it to go through if we need isoleucine. All right? If we don't need isoleucine, we want to stop it right here. All right. So the presence of threonine, all right, it actually activates the threonine dehydratase, and that will trigger the production of P1. So it basically activates its own metabolism to product here, okay? Now, so that would be under the situation where we have lots of threonine. Now imagine we have a situation where we have a high level of isoleucine. So I ask the question, if isoleucine, all right, so I'm just going to call it I, if it is high, do you want to keep producing it, right? So if I is a high concentration, okay, so that's what that up arrow means, right? Do we want to keep producing it? No, because we're not using it fast enough. So what happens is the isoleucine feeds back, and it binds to an allosteric site on our enzyme, and it prevents threonine from being converted to P1. It's an inhibitor. It's an allosteric inhibitor. we call this process feedback inhibition. And what it means is basically that if we've got too much of our isoleucine building up, we can stop the pathway that produces it, and so we call it feedback. Isoleucine feeds back and prevents its own production. All right, so that wraps up chapter 6, all right? And on Monday, we will be reviewing for Wednesday's exam.